The topic that we want to cover today is understanding when we have a nonlinear function. And we're going to understand this in the context of three scenarios that we're going to go through. But before doing that, let's take a look at the table of values below that shows us what the relationship is between the cost of attending an amusement park and the number of games played. And we want to write an equation for this. Remember, when we want to write an equation of a line, if we believe we have a linear relationship, we want to find the slope and y-intercept. Now, tying into what we're going to talk about today, how do we have a linear relationship? Well, we can see that the number of games is going up by 1 and the cost is going up by 2. So that's telling us there's a constant rate of change, and the rate of change is 2. So that is our slope. Now, what's our y-intercept? Our y-intercept is where x is 0 or where nothing has occurred, which is at a cost of 10. So how do we put this into a context of what is happening? It's costing $2 to play a game, and it costs us $10 to just get into the park. Is the relationship a function? Yes, because every x input has only one y output. Or you know it's a function because it's a linear equation. And as long as the line is a non-vertical line, and we know this would be a diagonal line because it has a slope of 2, we know it is a function. All right. Now, we want to demonstrate the concept of linear versus nonlinear through a couple of examples. All right. The area of a pizza is a function of its radius, as the area of any circular figure is. And the cost for the sauce is a function of how many ounces of sauce is used. Now, I want to complete this table based upon the varying measures of radius. And if you remember the formula, A equals pi r squared, that is the formula for area of a circle. I can convert this into y equals pi x squared, where x is the radius and y is the area. Completing this table using the formula, I get the following values. And I want to then graph them. So I'm going to move down here. You should know that the radius is my x-axis because it causes the change in the area. All right, I'm going to count by 2s, 2, 4, 6, 8, 10. And now I have to alter my y-axis a little bit to account for the fact that I've got a pretty wide dispersion of the numbers. 250 and 300. Sorry for the very poor writing. So now I'm going to graph this 0, 0, 2, and obviously it's not exact, but it's going to be good enough for what we need. 4 is a little bit above 50. 6 is a little bit above 100. 8 is a little bit above 200. And 10 is a little bit above 300. And we get a figure as such. Okay? Then I'm going to graph the weight. So it's 40 cents an ounce, or 80 cents for 2, $1.60, $2.40, $3.20, and $4. Excuse me. So I want to graph that relationship. Oh, let's get it to move. Orientation is a little off there. So the weight is the x-axis, and the cost is the y. I'm going to count my 2s here again. 2, 4, 6, 8, and 10. And then I'm going to have $1, $2, $3, $4. So And you'll see that we have the following. Oh, it's a little too high. 4 is about here. 6 is there. 8 is about there. And now, the question on the next page says, is each of these functions a linear function? Well, hopefully you can just see the easiest way to determine the answer to this is by the graph. And you should see that the graph in blue has a curve to it, but the graph in red is a straight line. So, by looking at the graphs, we can determine that is each no, the first is not. Now, I don't have this specifically laid out in your notes, but I do want to indicate this somewhere on your note sheet. If you might remember, we said a linear equation earlier in this course, okay, was an equation that would give us the graph of a line. And you notice that the x in a very simple linear equation like 2x plus 3 equals 9, the x is raised to the first power, while an equation like this is raised to the second power. This one is linear, this one is quadratic. Well, what makes a linear function in our example, or any example, if x and y are raised to the first power, then it is a linear function. So if you go back to the prior example, I rewrote the equation to be y equals pi x squared. Since x is squared, that is not going to give me a linear function. While in the second scenario, I could write this equation as y equals 0.4x, which is linear. Okay? Now, so far, the easy way is to figure out if the graph is linear. A second way to figure out is, does x or y have an exponent other than 1 when you write the equation? The third way is to look at a table of values. Now, if you look at this table of values, the x's are going up by 1, but the y's are not increasing by a constant amount. Excuse me. So, is this a linear function? Not a linear function. No constant rate of change. Okay? Now, I want to figure out, can I write a rule? Because this is a function, because every x has only one y. So I want to figure out, can I write a rule that makes this scenario true? Well, let's take these one at a time. All right? I can write the equation y equals x plus 1. That works here. Or y equals 2x. That works there. Or y equals 2 to the x power. So in all three of these equations, if I put 1 in for x, I'm going to get 2 for y. Now I go to the second one. The y equals x plus 1 doesn't work, but y equals 2x works, and y equals 2 to the x power works. So now I've got 2 candidates in the running. Now I go down to the third one. Well, y equals 2x doesn't work, but y equals 2 to the x power works. And you'll see it works here and there. So the function rule is y equals 2 to the x power. That is called an exponential function because the x is in the exponent place. Okay? We're going to deal more with exponential functions in the next unit, but just wanted to introduce the concept to you. Now, the question says, can every linear relationship be represented by a line when graphed? Yes. That's what the definition of a linear relationship is. All right? Now, last example. A local cheesemaker is making cheese. M is the amount of milk needed, okay, to get the weight in cheese. Okay? And I want to graph that relationship. So milk and weight, and I'm going to use a very simple 1, 2, 3, 4, and 4, 16, 32. Sorry about that. 48 and 64. So I'm going to graph these points. And I'm going to connect the dots for this because I don't need to just have whole amounts of milk. I can have partial amounts of milk and partial weights of cheese. Okay? Now let's contrast this with the next scenario where I'm going to graph. The A represents the number of wheels sold of cheese, and the N represents the money earned. So I'm going to have wheels sold, money, and I'm going to graph those points. 0, 0, 1, 9, 2, 18, 3, 16, and 4, 36. Now, the difference is I'm not going to connect the dots because what I have here is what's called a discrete graph, meaning I can't sell parts of a wheel. They can only be sold in whole units. And you might remember this from other examples we've done where, let's say it's shoveling sidewalks. I don't shovel parts of sidewalks. Or the number of people doing something. I don't have partial people. So a continuous graph is a graph that is unbroken. That's like the first one on the next that we just saw with the milk and the weight of the cheese. I can connect the dots there because I can have points in between that work. A discrete graph is a graph composed of distinct or discrete points, meaning only those points satisfy our conditions. Now, you will see discrete graphs where they will connect the dots to form a line, but you need to understand that not every point on that line works. Now, to tie this into what we did yesterday with functions, my domain or my x values. Will any value of x be able to be used? And remember, the x values in this scenario are the number of wheels sold. So can I sell any number of wheels of cheese? Hopefully you're saying to yourself, no, I can't sell negative numbers. I can't sell fractional or decimal numbers. So my domain is whole numbers, which is also what my range is going to be. And all I'm just tying that into is my domain is telling me what can my x values be. And in this case, my x values can only be whole numbers. So hopefully you've got a better understanding by looking at a graph, looking at a table of values, and looking at an equation as to whether you have a linear or a nonlinear function.